we've touched on the transformer before, like in case TCM 123001, but I'm still struck by the title of this paper. Attention is all you need. That's a bold claim.
It truly is, Maya. It challenges the prevailing wisdom that sequence tasks needed recurrence or convolutions. It suggests that a simpler, more elegant mechanism could do the heavy lifting.
The paper makes this clear from the start. They propose a new, simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely.
So no more RNNs trying to remember long sequences or CNNs needing to scan local regions? Just attention? That sounds almost too good to be true.
The magic is in how that solely attention part leads to huge practical benefits. Recurrent models are inherently sequential. They process one token at a time.
Right, because each step depends on the previous one. That's a bottleneck for speed, especially with large data sets.
Exactly. But the transformer, by focusing on attention, became more parallelizable and requiring significantly less time to train, as the authors noted.
This wasn't just a theoretical win. On the WMT 2014 English to German task, it achieved improving over the existing best results, including ensembles, by over 2 blue.
So faster and better. That's the kind of double win that truly shifts a field. But how can attention alone capture all the complexities of language?
That's a key question. Often when we think of attention, it's about focusing on a small part. But here, it's about dynamically forming connections across the entire input simultaneously.
I see. It's not just about picking one important word. It's about how every word relates to every other word, all at once?
Precisely. The efficiency gains meant they could train a model to a new single-model state-of-the-art BLUE score of 41.8 after training for 3.5 days on 8 GPUs.
That's incredible. So this paper isn't just about a new model. It's about a paradigm shift in how we approach sequence modeling, thanks to attention.
It opened the door to thinking about sequences in a fundamentally different way. Now, let's peel back the layers to understand how this attention mechanism actually works.
I'm ready. My intuition about attention feels a bit fuzzy. I'd love to solidify it, especially for how it became all you need.
This diagram from the illustrated transformer is fantastic for building intuition. At a high level, the transformer has an encoding and decoding component.
I see. It looks like a classic encoder-decoder, but instead of one, it's a stack of encoders. 6 of them here. Is that important?
You astutely noticed the encoder-decoder structure, Maya. While the encoder uses self-attention to understand the input sentence, the decoder has an additional trick up its sleeve for tasks like machine translation.
Is that the attention layer mentioned between the 2 sublayers in the decoder?
Exactly. That's cross-attention. It's an attention layer that helps the decoder focus on relevant parts of the input sentence from the encoder's output. So, when the decoder is generating a word in the target language, it can look back at the entire source sentence to pick out the most relevant parts for its current prediction.
So, self-attention within the encoder builds context for the input, and cross-attention in the decoder links that context to the output generation. It's like the decoder is constantly referencing the entire source document.
The stacking provides depth, allowing for richer representations. But the key is what's inside each encoder. The source says each one is broken down into 2 sublayers.
Okay, 2 sublayers. One is self-attention, and the other is a feed-forward neural network. This self-attention again. If there's no recurrence, how does the transformer know the order of words? Animal tired it means something totally different than it tired animal.
Excellent question, Maya. That's where positional encoding comes in. Before the word embeddings enter the encoder, we add a special vector to each word embedding that encodes its position in the sequence. These aren't learned during training, they're fixed patterns that allow the model to infer word order, ensuring animal tired it is processed differently from it tired animal.
So it's like tagging each word with its spot in the lineup, making up for the lack of sequential processing without losing the benefits of parallelization.
Let's use their example. The animal didn't cross the street because it was too tired. What does it in this sentence refer to? For a computer, this is hard.
Naturally, it refers to the animal. A human gets that instantly, but for a language model, street is closer. How does self-attention solve this?
When the model processes it, self-attention allows it to associate it with animal. It computes a relevance score between it and every other word.
So it's not just taking the closest word, but understanding contextual relationships. That's what gives it the all-you-need power, right?
Exactly. Instead of a single, fixed, hidden state like an RNN trying to summarize everything, self-attention is the method the transformer uses to bake the understanding of other relevant words into the one we're currently processing.
So in case TCM-093005, we saw self-attention's parallelism. Now I'm seeing its dynamic contextual understanding as the real secret sauce.
It's crucial to note that while the feed-forward layers operate fully in parallel on each word, there are dependencies between these paths in the self-attention layer.
Wait, if there are dependencies, how is it so parallelizable? Doesn't that slow it down?
The dependencies are computed simultaneously across all words through matrix operations. Unlike RNNs, where each step waits for the previous, self-attention evaluates all dependencies at once.
So the list of vectors representing the input gets processed in parallel through self-attention, then through the feed-forward network. That's the core.
That's the high-level picture. Now, let's zoom in on self-attention in detail and see how those relevant scores are actually calculated using query, key, and value vectors.
I'm ready for the technical deep dive. How do query, key, and value come into play to make this contextual understanding possible?
The first step in self-attention is critical. For each input word vector, we create 3 vectors: a query vector, a key vector, and a value vector.
So every word like animal or it gets these 3 distinct representations. What do they represent intuitively?
Think of it like searching for videos online. Your query is what you type into the search bar. The keys are the metadata or tags on all available videos.
And the value would be the actual video content. So my query searches against all keys to find relevant values. It's a useful way to think about how relevance is found. However, where this analogy starts to break down is that in self-attention, we don't just retrieve one or a few relevant values. Instead, we blend all values together, each weighted by its relevance score, to create a new context-rich representation. And crucially, every word in the input sequence acts as its own query, key, and value.
Precisely. The second step is to calculate a score. The score is calculated by taking the dot product of the query vector with the key vector of every other word.
So, if I'm processing its query vector checks against the key vector of animal, street, tired, and so on. A higher dot product means more relevance.
Yes. So,
If we're processing the self-attention for the word in position number 1, the first score would be the dot product of Q1 and K1, then Q1 with K2, and so on.
This explains the parallelism. All these dot products can be computed at the same time for a single query and for all queries across the sequence.
Next, we divide the scores by 8, specifically by the square root of the dimension of the key vectors, which was 64 in the original paper, so SQRT64 equals 8. This scaling is crucial because without it, large dot products could lead to extremely large values, pushing the softmax function into regions with vanishing gradients, which hinders effective learning. After scaling, we pass the result through a softmax operation.
Softmax normalizes them, so the scores become probabilities adding up to 1. This tells us exactly how much to attend to each word.
That's exactly right. This softmax score determines how much each word will be expressed at this position. It's the learned interpolation we talked about in previous cases.
So for it, the softmax score for animal would be high, and for street it would be low, indicating that animal is more relevant.
The final steps are to multiply each value vector by the softmax score and then sum up the weighted value vectors. This produces the new context-aware representation for that word.
The value vectors carry the actual content. We're essentially blending the content of all words weighted by their relevance to the current word. Fascinating.
While incredibly powerful, this self-attention mechanism isn't without its considerations. Notice how we calculate the dot product of every query with every key. That means if our input sequence has length L, this calculation is proportional to L squared. For very long sequences, this quadratic complexity can become a significant computational bottleneck, making it slow or memory intensive.
Aha, so while it's highly parallelizable, there's still a practical limit to how long a sequence it can efficiently handle. That's a crucial trade-off to understand.
This detailed self-attention mechanism, repeated in multiple layers, is what allows the transformer to build rich, contextual representations without sequential processing. But the original transformer didn't just use one of these attention heads.
Oh, there's more? I thought one attention mechanism was all you need. What else did they add?
Now, the transformer doesn't just use one set of query, key, and value projections. The original paper introduced multi-headed attention.
Multi-headed? Like having several QKV systems running in parallel?
Precisely. Instead of performing self-attention once, it does it multiple times in parallel, each with different, independently learned Q, K, and V projection matrices. Each head learns to focus on different aspects of the input. One head might focus on syntactic relationships, another on semantic ones, or even the object-verb relationships.
So it's not just one way of looking at relationships, but many different perspectives simultaneously? That sounds incredibly powerful for capturing nuanced meanings.
It truly is. After each head computes its own set of weighted value vectors, these are concatenated and then projected down to the expected output dimension. This gives the model a richer, more comprehensive understanding of the input from various representation subspaces.
So multi-head attention amplifies the contextual understanding, allowing the transformer to consider a wider range of dependencies and meanings. It's like having a team of experts, each with a different specialty, all analyzing the same sentence.
A perfect analogy, Maya. And that's why it's a core component, making the transformer so robust.
With the full power of positional encoding, self-attention, cross-attention, and multi-head attention, transformers reshaped natural language processing. But what about images? Could this text-centric architecture really translate to vision?
That's still the big question on my mind. Images don't have words or a clear sequence. How does a transformer see a picture? So we have this powerful transformer for text, but for years, vision was dominated by convolutional neural networks. This paper, an image is worth 16 by 16 words, seems to challenge that.
It absolutely does. The abstract starts by acknowledging that while transformers were de facto for NLP, its applications to computer vision remained limited at the time of its writing.
Their core idea is remarkably simple. Treat an image not as a 2D grid, but as a sequence of flattened 2D image patches. These patches are then fed into a standard transformer encoder, just like words in a sentence.
So, instead of words, we have image words or visual tokens. They're chopping up the image into smaller, digestible pieces.
Exactly. For example, a 224 by 224 pixel image might be divided into 16 by 16 pixel patches. Each patch is flattened into a 1D sequence of pixels, which then becomes a vector, much like a word embedding.
And just like with text, they'd add positional encodings to these patch vectors, so the transformer knows where each patch is located in the original image?
Precisely. Without positional encodings, the transformer wouldn't know if a patch belongs to the top left corner or the bottom right. It's crucial for reconstructing the image's spatial information.
This transformation allows the powerful self-attention mechanism, which excelled in capturing long-range dependencies in text, to do the same for visual information. It can correlate a pixel in one part of an image with pixels far away, something traditional CNNs might struggle with without many layers.
So a VIT can understand relationships between distinct objects or regions in an image more directly, similar to how it connects it to animal across a sentence.
While VITs achieve impressive results, they also come with a significant consideration. Unlike CNNs, which have built-in inductive biases like locality and translation invariance, meaning they inherently understand that nearby pixels are related and that an object looks the same regardless of where it is in the image, transformers don't have these.
So a VIT starts almost tabula rasa with images? It doesn't have that prior knowledge about how images are structured?
Exactly. This means that to learn these fundamental visual patterns from scratch, vision transformers typically require vastly more data for pre-training compared to CNNs to achieve competitive performance. Without massive data sets, their performance can lag behind. It's a trade-off, immense flexibility versus data-hungry training.
That makes sense. CNNs are specialized for images, while VITs are generalists adapted to images. The specialization comes with efficiency, the generalization with data demands.
And that's the journey of the transformer, from revolutionizing text processing to becoming a powerful contender in computer vision. It underscores how fundamental mechanisms, when reimagined, can transcend domains.
It's truly a testament to the power of abstraction and parallelization. Attention is all you need isn't just a catchy phrase. It's a testament to a flexible foundational primitive.